What specific problem does your proposed Samurai method address in the context of visual object tracking, VOT, and how does it improve upon the limitations of SAM2?
The proposed Samurai method addresses the limitations of SAM2 in visual object tracking, VOT, by incorporating motion information and optimizing memory management to enhance tracking accuracy in complex scenarios. SAM2 struggles with maintaining consistent object identity and location during occlusions and rapid movements, often neglecting motion cues and prioritizing appearance similarity, which leads to tracking errors, especially in crowded scenes. Samurai improves upon this by implementing a motion modeling system that refines mask selection based on object trajectories, allowing for more accurate predictions of object positions. Additionally, it introduces a motion-aware memory selection mechanism that utilizes a hybrid scoring system, combining mask affinity, object occurrence, and motion scores to selectively store relevant frames, thereby reducing errors during occlusions. These enhancements enable Samurai to achieve state-of-the-art performance across various VOT benchmarks without requiring additional training or fine-tuning.
How does the proposed method Samurai work? Illustrate the core components and processes step by step, particularly focusing on the motion modeling and memory selection mechanism.
The proposed method Samurai enhances the segment anything Model 2, SAM2, by integrating two core components, motion modeling and a motion-aware memory selection mechanism. First, the motion modeling utilizes a Kalman filter, KF, to predict the bounding box's position and dimensions based on the object's trajectory, allowing for the selection of the most confident mask from multiple candidates. This process involves defining a state vector that includes the bounding box's center coordinates and dimensions, and calculating a potassium fluoride IOU score to evaluate the predicted masks against the bounding box. Second, the motion-aware memory selection mechanism improves the original fixed-window memory approach by employing a hybrid scoring system that combines mask affinity, object occurrence, and motion scores. This selective approach ensures that only frames meeting specific thresholds for all three scores are retained in the memory bank, thereby enhancing the model's ability to handle occlusions and complex interactions in crowded scenes. By integrating these components, Samurai effectively improves tracking accuracy and robustness without requiring additional training or fine-tuning, demonstrating strong generalization across various visual object tracking benchmarks.
Can you provide a simple, illustrative example demonstrating how the motion-aware memory selection mechanism operates in a typical video tracking scenario?
In a typical video tracking scenario, consider a scene where a red ball moves through a crowded park filled with similar-looking objects. The motion-aware memory selection mechanism operates by evaluating past frames based on three scoring criteria: mask affinity score, object occurrence score, and motion score. For instance, if the red ball is occluded by other objects, the mechanism will look back at previous frames and select those where the ball was clearly visible and moving in a consistent trajectory, ensuring that the selected frames meet the defined thresholds for all three scores. This selective approach allows the model to retain relevant historical information about the red ball's motion, thereby enhancing the accuracy of mask predictions and reducing tracking errors in complex scenarios. Ultimately, this results in a more reliable tracking performance, even in the presence of similar objects and occlusions.
What are the main theoretical and practical benefits of the Samurai approach compared to existing state-of-the-art methods in VOT, according to your experimental findings?
The Samurai approach offers significant theoretical and practical benefits over existing state-of-the-art methods in visual object tracking, VOT. Theoretically, it enhances tracking accuracy by integrating motion modeling with a hybrid scoring system that combines mask affinity, object occurrence, and motion scores, allowing for more reliable mask selection in complex scenarios, particularly during occlusions and rapid movements. Practically, Samurai achieves state-of-the-art performance on multiple benchmarks, including LOS-OT and GOT-10K, without requiring additional training or fine-tuning, demonstrating its strong generalization capabilities across diverse datasets. Experimental results indicate that Samurai consistently outperforms the baseline SAM2 model, achieving significant improvements in metrics such as AUC and P_norm, particularly in challenging conditions like full and partial occlusions. Furthermore, the incorporation of motion-aware memory selection minimizes computational overhead while maintaining runtime efficiency comparable to the baseline, making it a robust solution for real-time applications in VOT.
How was the effectiveness of Samurai validated in the experiments? Discuss the datasets used, the metrics for evaluation, and the experimental design.
The effectiveness of Samurai was validated through extensive experiments on several visual object tracking (VOT) benchmarks, including LOSOT, LOSOT_Ext, GOT10K, Tracking Net, NFS, and OTB100. The evaluation metrics used to assess performance included average overlap (AO), overall precision (OP), and area under curve (AUC), which provided a comprehensive view of tracking accuracy and robustness. The experimental design involved a zero-shot evaluation protocol, allowing Samurai to demonstrate its generalization ability without additional training or fine-tuning, thus comparing its performance against both zero-shot and supervised methods. Results indicated that Samurai consistently surpassed state-of-the-art performance across all metrics on the tested datasets, showcasing significant improvements in challenging scenarios, particularly in handling occlusions and fast motion. Additionally, the experiments included a detailed analysis of the impact of individual modules, demonstrating that both motion modeling and memory selection positively influenced tracking performance.
What specific results were achieved with Samurai on the LOSOT and GOT10K benchmarks, and how do these results compare to those of SAM2 or other baseline methods?
Samurai achieved significant improvements on the LOSOT and GOT10K benchmarks compared to SAM2 and other baseline methods. On LOSOT, Samurai demonstrated state-of-the-art performance, surpassing both zero-shot and supervised methods across all metrics, with a notable AUC of 74.23% and P_norm of 82.60%. In the GOT10K dataset, SAMURAIB showed a 2.1% improvement in average overlap (AO) and 2.9% in overlap precision (OP_0.5) over SAM2. Furthermore, all Samurai models consistently outperformed the state-of-the-art on all metrics in both datasets, showcasing its strong generalization ability. These results highlight the effectiveness of the proposed motion modeling and memory selection mechanisms in enhancing tracking performance in challenging scenarios.